Hello folks, and welcome to this lesson on organic nomenclature, alkanes. By the end of this lesson, you should be able to name and draw straight chain alkanes with various side chains. So welcome to the first in a relatively longish series of lessons around organic nomenclature. Now before we actually go into the different types and so on and so forth, what are organic compounds? Well, these are compounds that are based mostly on carbon and hydrogen, and they are also referred to as hydrocarbons. You're probably going to hear me use the term organic compound and hydrocarbons fairly interchangeably. Now, is it just about the carbons and hydrogens? No, you can also get different elements in there, such as halogens, oxygens, nitrogens, sulfur, and other elements as well. Now, this being said, the ones that you're going to see the most in this course are probably going to be halogens, oxygens, and nitrogens. And in terms of the reactions that you're going to see, most of them are going to involve oxygen. So, you have carbons, which you can link in very, very many different ways because each carbon can have up to 4 connections. You have all these other elements that you can put in here. You have double bonds and triple bonds that can happen with not just the carbons, but also with the other elements. So there is a lot of variety that can happen in organic compounds. And because of that, that's sort of why it even has its own naming system. And if you go to higher education and you go into chemistry, you're going to see that a lot of the times your chemistry courses are going to be divided into the physical chemistry, which is pretty much all of the chemistry that you've done up until this point in your academic career. And then you'll have organic chemistry, and it is its own beast, which we are sort of going to get a bit of a view on. So we're going to start with the simplest type of hydrocarbon, which are alkanes. Now, alkanes are also referred to as being saturated in that when you have all of your carbons, there are only single bonds between them. Now, not only are there mostly, or pretty much only single bonds between carbons, you're mostly also dealing with just carbons and hydrogens if you're talking about alkanes specifically. Alkanes generally have the generic equation of CnH2n+2. Now, if N is the number of carbons, you can figure out how many hydrogens it's going to have based on this equation. Now, this is not going to hold true if you have any halogens in there, and it's also not going to hold true if you have a cyclic hydrocarbon, but this is the very, very generic equation for a straight chain alkane. Now, the base name of an alkane is going to depend on how many carbons is in that main chain. So here I have a table of what those names are. You are going to have to memorize these, and these are going to keep on showing up in pretty much all of the other type of nomenclature that we do, because the prefixes are very much tied to the numbers of carbons. And so what's going to happen when you're doing this naming is, depending on what side chains and what other functional groups you have in your hydrocarbon, you're going to be changing your suffixes and you're going to be adding stuff to the beginning. But then the base, here's how many carbons my base chain, my parent chain has, is pretty much going to follow these names. Now, when you're trying to memorize these, some of these are going to be easier at first than others. Pentane, penta, pentagons, 5-sided shape. Hexane, hexagon, same sort of thing. Octagon, octopus, octopuses have 8 arms. Nona, nonane. Nano is like 10 to the negative 9. So nanometers is 10 to the negative 9 meters, and so on and so forth. Decane, you've also seen before. Decade, it means 10 years. So that deca refers to 10. The ones that are a little bit harder to remember are probably going to be heptane. You don't deal with 7 things that are numbered as 7s very often, but there you go, that's heptane. But the most challenging is probably going to be the first 4, where you have methane, ethane, propane, and butane. They don't really have common analogs in other numbered things that you've dealt with. However, the way that my chemistry teacher taught it to me when I was back in high school in the day, is you take MEPB, monkeys eat peeled bananas. And so that's how I remember the first four. I'm going to emphasize again, it is important to know all of these names. Now, when you're drawing your organic compounds, there are many sort of typical or accepted ways of drawing it. These are the three that you're going to be expected to be able to use. Now, as an example of how each of these are going to work, I'm going to draw butane for you. I don't remember if the IB specifically wants you to be able to draw a specific method, so I don't know if they'll specify which method that they want you to use. But if you're not taking an IB course and it's me marking everything that you're doing, then no worries. I don't care which one of these you use. You need to be able to recognize them and you need to use them properly. That's all. All right, for the first one, you have your full structural or expanded structural method of drawing. So for this one, you are drawing every single element and every single bond. So with butane, that's going to be C4H10. And so you're going to be drawing every single carbon and every single or double or triple bond, depending on the type of compound you have. A benefit to this particular structure will be the fact that you can keep track of all of the bonds that each element has, so you're probably not going to be missing something. But the downside is going to be there's a lot of drawing that goes in there. For the condensed one, what happens is that you are going to have all of the carbons and you are going to write all of them, and you do end up writing all of the hydrogens as well, but you take advantage of the fact that all of these carbons are going to have hydrogens attached to them. The difference is going to be how many and are there other bonds. So the condensed version of butane is going to look like this. I've drawn two versions of this, one with single bonds between each of those carbon-hydrogen groupings. If you're going from left to right, you're sort of going horizontally, you don't necessarily have to draw in those bonds. If you are going up and down from here, you do want to draw in those bonds, but if you're just going left to right, then you don't really have to. Now you can see here, it's easy to see what the groupings are and where all the hydrogens are going, so it is easier to keep track of what some of these functional groups are without losing track of where the hydrogens are as well. Now my favorite is the skeletal or line, and you'll see why. This is what a line diagram looks like. You can see how simple it is. And there are benefits to why these are drawn these way as well. So at the end of every line and at these corners, every one of them is a carbon. If it were a different element, you would write down the symbol of the element. So for example, if you were going to draw one that had oxygen in the middle, it might look something like this, where you have oxygen there and then carbon, carbon, carbon. You assume that if there isn't anything else, all of the remaining bonds that that carbon could make out of its four are going to be hydrogens. So it takes out a lot of the bulk of the other diagrams, and you sort of get to the point of what is going on with that structure. And if you have very complex structures, it makes it a lot easier to see as well. The reason why it's drawn with a bent line and those angles aren't 90 degrees is because of Vesper theory. So we're going back to that old Vesper theory because that is what is actually happening in these structures. Your carbons are basically always going to have four things attached to it, unless there's a double bond involved in there, which we will get to. And so based on Vesper theory, it's always going to be a tetrahedral structure around that carbon, again, assuming that you only have single bonds. So those angles are not going to be 90 degrees. They're actually going to be 109.5. And so because of that, you do draw it as a crooked line because when you attach several of these carbons together, that's what's going to happen. You're not really going to find if you turn it a specific way. You are going to see that it does become a straight line like this, but in all honesty, you look from every single other angle, and you're going to see a bent line. So that's why these skeletal drawings are based on lines that have corners in them. Now, as I mentioned, when it comes to an organic compound, it's not always going to be your singular straight line. You can also have things branching off of those lines as well. So, for example, you can have alkyl groups. Alkyl groups are basically alkene or alkyne groups. They're just carbon chains that have hydrogens on them. There are certain aspects of branching that we're going to deal with, but not super complex ones. So don't worry about that at this point. And when you're naming these as a side chain, you're basically going to take the alkane name and change the ending into YL. So if you have a branching chain that has one carbon in it, then that's going to be referred to as a methyl group. The other type that you're going to see in this lesson are going to be halogenoalkanes. So you'll have halogenogroups, which are basically halogens. Sometimes I also refer to them as halides. And in that case, it's basically just a halogen. It's attached, and then you take the halogen name and add O to the end, and that's the side chain name. If you remember, halogens typically only form a single bond. So a single bond. And so you're not really going to have more chains that evolve from where that halogen is. So fairly simple. Here are a few more terms that you're probably going to encounter as we go through the different lessons on nomenclature. We're not going to touch upon these much right now. You have your homologous series, which are basically a family of compounds where successive members all differ by a common structural unit. So basically, all of the alkanes are a homologous series. All of them are straight chains, and you only increase it by a carbon with 2 hydrogens. All of the alcohols, if you're just adding a carbon into each one of those chains, all of them are going to be a homologous series, and so on and so forth. We have different types of isomers. We have structural and constitutional isomers, same formula, different connections. So you can have things where you have chains that are built in different ways, single chain versus having a side chain, that sort of thing. Or you can put the side chains in different ways, and those will also be structural isomers. Stereoisomers, you have the same connections, but you have different arrangements. And I'm not going to say any more than that in this particular lesson. Now, when it comes to the name of an organic compound, this is basically the formula for how it's set up. So, at the very, very beginning, you'll toss in the stereoisomer kind of information, if it is relevant. Then you're going to have your side chains with its prefixes and its carbon number. If it's cyclic, the cyclo goes in here. Then you start the parent chain name. You start with the part that reveals the number of carbons in there. Any info on unsaturation also goes there. And then at the very end, it's going to be your suffix, which is based on your most important parent functional group. For example, here, we have no stereoisomer info, but here is the info on the side chains. There's no cyclo, so it's not cyclic. We know that the parent chain has 6 carbons in it, and then we have a double bond in there, and then it's also an aldehyde. You're going to see more of this and how it works as we go through, but for now you can write this down and then refer to it as we do and add on to it. Now, the easiest way to draw an organic compound is based on these steps. I'm not going to go through them right now. I'm going to show you how they work as we do some practice. I do have an asterisk here, and that's because of the fact that in 2013, IUPAC, which is sort of the global organization for everything chemistry, they changed the naming methods of organic compounds. So technically, all of the rules that I'm telling you are not true IUPAC rules. They are based on old IUPAC rules, but generally it takes a while for these rules to get to the education level. If you've ever heard me rant about STP, then you'll know that this is always the case. And even I only know 1 or 2 things about the new rules because they're also behind a paywall. You have to pay to find out what those new rules are. So, now one last thing that I want to say before we start trying to draw these hydrocarbons is make sure you are drawing your connections correctly. I don't want any carbons being bonded to like the middle of a bond. I don't want any carbons being bonded to hydrogens of something else. So none of this kind of thing, none of this kind of thing. This is where you want to aim for. Make sure all of your links are going between the carbons. All right, so here we go. We have our name. So first thing we want to do is draw our parent chain. Our parent chain is right at the back here. It's octane. So octane means it's going to be 8 carbons and no double bonds. And start from one side, number your carbons. I'm going to go left to right because I grew up using texts that go left to right. Now our parent chain is just an alkane, so there's nothing else going on there. So let's go on to our side chains. So we have 2,2-dichloro. So on carbon 2, we have 2 chlorines. And then we have our 5 propyls. So on our 5th carbon, we have a propyl group. Propyl refers to 3, so that's going to have 3 carbons. Everything's taken care of. Now we're going to toss in all of our hydrogens. So this is going to be the condensed formula. If you just make sure, the one thing to make sure is you're writing in the correct number of hydrogens. Don't write in too many, forgetting that you have a side chain or something like that. If you want to go with a line structure instead, I would go, okay, so we have 8 carbons, 1, so that first putting your pen on the paper is your first carbon, 2, 3, 4, 5, 6, 7, 8. Count to confirm, 1, 2, 3, 4, 5, 6, 7, 8. And then we have our 2,2-dichloro. Now we're going to do some Vesper stuff, so our chlorines are going to here. And then on our 5th carbon, 1, 2, 3, 4, 5, we're going to have a 3 carbon chain. So we start here and then it's 3 more carbons. And so that's what it would look like as a line structure. Now, do you have to show all of the numbering and all of the steps that you're taking when you're doing this for an evaluation and you're drawing something that they tell you to draw? No, you don't have to do any of that. Once you get used to drawing these, you probably won't have to physically number things as you did in practice. Here are the methods. Here is the method to name an organic compound. I'm not going to go through this right now. We will go through it as we go on with all of these lessons in organic nomenclature. Same asterisk for the same reason as before. I do want you to be aware of ones, and I will go over that with some examples as it becomes relevant. All right, so here's our structure. The first thing that we're going to do is we are going to identify the parent chain. Now we can see that all we have are carbons and halogens, so that means we're going to be dealing with an alkane. So we're going to find the longest alkane chain, the longest carbon chain, that will be our parent chain. So in this particular case, you could go this way. You could also go up from here. It doesn't really matter. It's still the same number of carbons. Then you're going to number your carbons. You could go 1, 2, 3, 4, or it could end up being 1, 2, 3, 4 from the right. So which one is it? There usually is a correct answer. For that, since we have no other functional groups, we're going to go for our side chains. So we have a side chain here, and a side chain here, and a side chain there. So if we look at the numbering of the side chains, if we go from 1 to 4 this way, then our side chain numbering would be 2, 3, 3. If we were going to go from right to left, it would end up being 2, 2, 3. Now if you look at these number combinations, 2, 2, 3 is the smallest number combination. So we're going to be going from right to left. From here, I typically like to make a note of what the names of each of the side chains are because it helps me with that whole last part, which is putting the whole name together. So no stereoisomer information, side chain information. Side chains always go in alphabetical order of the side chain name. So in this case, we have chloro and we have methyl. So we're going to go with chloro first. We're going to put in the numbers, and so in this case, it's going to be 2, 3. There is a comma between the two numbers because you could theoretically have a 23 in there. So you have 2, 3. There are no spaces between any of this. After that, we put in the name of the side chain plus how many of it we have. So in this particular case, we have 2 chlorines, so it's dichloro. Then we have our other side chain, which is our methyl group. That's the end of our side chain, so we're going to put in the name of our parent chain, which is going to be butane. Now note there's no dash between your last side chain and the name of your parent chain. There's no space either. There is technically no space in any of this name, so some of these organic chemistry names are going to look pretty ridiculous. So there you go. That's your first lesson on organic nomenclature. I'll see you next time.